Hello students, welcome back to another lecture of environmental modeling and simulation, and we are going to look at a fascinating kind of bifurcation which is known as transcritical bifurcation. This is a kind of bifurcation, as I mentioned at the end of our previous lecture, in which at least one of the fixed point is never destroyed or not created. It's always there. It may change its stability, but that fixed point always exists. And the example I gave you was of the logistic growth or any kind of growth actually, where 0 is always going to be a fixed point. And it is also true with what we observe in our labs, that if there is no initial quantity of organisms, we cannot grow them. So, the first example that I'll give you for transcritical bifurcation is actually a model that will remind you of logistic growth. So, here is our example. dx by dt is equal to rx minus x square. So, if you remember logistic growth, the first term and the second term, the first term is about the exponential growth and the second term is where the carrying capacity comes in. Okay. So, if we want to look at how this system changes when we change the parameter, now notice one thing, in logistic growth there are two parameters r and k. I have written this in a way that we only have one parameter here, which is r, to make our life easier. If you have multiple parameters, you need to vary each one of them and see how your system behaves, how your fixed points change, whether they appear, disappear, collapse, change their stabilities. So, to make this example easier, I have only put one parameter, rx minus x square, and it is possible to write our systems in a way that we reduce the number of parameters. So, this very well could be a logistic growth model. Okay. So, to understand how the system behaves as the r changes, we need to find the fixed points. So, dx by dt is equal to 0, which means taking x common, this has to be 0. So, what we are left with is either x is equal to 0 or x is equal to r, right. So, let us take the example when r is positive, which we are very familiar with. So, let us say x on x axis, dx by dt on y axis, and one fixed point is 0, another fixed point here is r, and our growth looks like this. Yeah. On left side of the first fixed point, which is 0, dx by dt is negative, here it is positive, and here again it is negative. So, we know this is an unstable fixed point, 0 is an unstable fixed point, and here we have a stable fixed point, which is basically what the carrying capacity would be. Okay. Now, let us change the value of r. Let us take r at, let us start reducing r. So, we are taking r from positive all the way to r that is negative. So, when r becomes negative, this is how our system will look like. 0, and then here we have r, and x is on x axis. Our system will look like this. So, notice here on left side of the r, dx by dt is negative. So, the flow is to the left towards minus infinity. Here it is towards right, towards plus infinity, again towards left on the right side of 0. So, 0, which was an unstable system, unstable fixed point, when r is less than 0 becomes a stable fixed point. But 0 is still there, it does not go away, and r becomes an unstable fixed point. Of course, we want to know what happens in middle when r is equal to 0, then there is only one fixed point, which is x is equal to 0, and the curve looks something like this. Now, notice what is happening here. On left side of this fixed point, x is equal to 0, dx by dt is negative. So, the flow will be towards left side going towards minus infinity. On right side of the fixed point, dx by dt is also negative. So, the flow will be towards left side. So, what we notice here is that this is a half stable, half unstable fixed point. On right side, it is a stable fixed point. On left side, it is an unstable fixed point. So, notice what happens here. Unlike saddle node bifurcation, when the two fixed points collapse into one, and then we keep changing the value of r, the fixed points do not disappear. In saddle node bifurcation, the fixed points were disappearing. What is happening is one fixed point is always there, which is 0. The other fixed point moves on the other side of your coordinate axis, and the stabilities switch. This kind of system is known as transcritical bifurcation, and this is the kind of system that we see a lot in our environmental systems. So, what we notice here is that x equal to 0 is a fixed point that we never lose. Even when the fixed points collapse, this fixed point is there. And this is typical of growth models. Now, let us try to summarize this in a single diagram, where we will plot the parameter on x-axis and fixed points on y-axis. Now, notice R critical, the critical value of the parameter where bifurcation starts showing its behavior. We know the value is 0. It was very easy to figure this out. We did not have to differentiate and find the tangential point of any two meeting curves, intersecting curves. So, at R equal to 0, we know that there is only one fixed point, and we know that on the positive end it is stable and on the other end it is unstable, negative end. When R becomes less than 0, we have two fixed points. So, 0 is always a fixed point. So, the x-axis will always be a fixed point in this diagram. However, when R is less than 0, the x-axis, which is x is equal to 0, the fixed point is x equal to 0, becomes a stable fixed point. And when R is greater than 0, x equal to 0 is an unstable fixed point. And I would like to show that using a different color. So, let us take red. So, when R is negative on left side here, we are going to have x equal to 0 a stable fixed point, and I am going to show it by a line to show the stability. Typically, when I teach this course in the class, I ask students to bring their markers or their crayons to use colors to show the stability and instability, especially when we have a case like this where your line intersects one of the coordinate axes. When R is greater than 0, x equal to 0 fixed point becomes an unstable fixed point. So, we show it by dashed line. So, this is very simple. Now, let us look at another fixed point, which is x is equal to R. So, x is equal to R is not a curve, it is a line. So, the second fixed point will act like a line. When R is greater than 0, when R is greater than 0 in this side, then x is equal to R is a stable fixed point. So, what we are going to see is, as R increases, this will increase, the slope will be 1. So, it is a stable fixed point. When R is less than 0, x equal to R is an unstable fixed point. So, we can show it using dotted line. So, this is our example of transcritical bifurcation. Let us look at another kind of bifurcation, which is pitchfork bifurcation. The pitchfork bifurcation is called so because of the kind of diagrams we make. In fact, we can call it pitchfork trifurcation, and we will soon find out why. Now, pitchfork bifurcation is very important for systems that are symmetric, and there are multiple systems that I can think of right away which are symmetric either left to right, or if you replace x with minus x, the system does not change. For example, in the buckling example that I gave when I introduced bifurcation to you, once the column, so let us say we have a column here and we have heavy load on top of the column. Once the column reaches the threshold, as we are changing the load parameter, the parameter we are changing is the load here. As we are increasing the load, the buckling can happen on left side or right side. So, there are two possible solutions. One is to the left, one is to the right. So, the column is symmetric on left and right side. In these kind of systems, we notice pitchfork bifurcation. So, what is happening in pitchfork bifurcation is that new fixed points are appearing or disappearing. In case of buckling, one fixed point will show buckling towards left, a new fixed point will show buckling towards right. But these new fixed points that appear or the fixed points that disappear, they always do it in pairs. There is a symmetry there. Okay, so let us take an example of pitchfork bifurcation. The example that I am going to take here is dx by dt is equal to Rx minus x cube. And there is a reason why I am taking this. It is typically also the first example that is taught of pitchfork bifurcation. And the reason is that it is an example of supercritical pitchfork bifurcation. Now, as I mentioned, symmetry is a very important aspect of pitchfork bifurcation. In this particular example, if I replace x with minus x, let's take a look at what happens. So, if I replace x with minus x, this is what happens. Take the minus from LHS to the right, and we come back to what we started from. So, basically this system is symmetric when we replace x with minus x. So, this system is, if I look at this system, I can be like, it may go through pitchfork bifurcation. So, let's figure it out. So, to figure out the behavior of this system as I change the parameter, first I need to find the fixed points. To do that, dx by dt is set equal to 0. So, here we have 3 fixed points, possibly 0 and plus minus under root r. Just by looking at it, you can already tell if r is negative, we are not going to get fixed points. If r is positive, we are going to get fixed points. So, without even needing to draw the full phase portrait, dx by dt on y-axis, x on x-axis, let's take the case when r is positive. When r is positive, we have 3 fixed points, x equal to 0, x equal to minus under root r, and x equal to plus under root r. So, now what we need to do is we need to find out the sign of the curve, this curve around the fixed point. So, when x is greater than r, under root r, then the curve will be less than 0, dx by dt will be less than 0. So, it will look like this. When x is between 0 and under root r, it will be greater than 0, and when x is between the first fixed point minus under root r and 0 less than 0, on left hand side of the first fixed point greater than 0. So, very easily we can understand the flow here, we can understand the stability. Whenever dx by dt is positive, the flow is towards right because x is increasing. Here x is decreasing between the first and the second fixed point. I am calling this one the first, 0 is the second, and this one is the third one. And remember, we are looking at r greater than 0. So, the flow is towards left, here the flow is towards right and towards left. This fixed point is a stable fixed point, unstable fixed point, and another stable fixed point. Okay, now let's change the value of r. We are making r equal to 0. When r is equal to 0, or as r moves from a positive value towards 0, what will start happening is that these two fixed points will start moving towards 0. Already I can see that they are going to collapse into 0. So, as they start moving close to 0, the peaks of this curve will start moving close to 0, may even become small in magnitude, and eventually what we will see is something like this. So, when r is equal to 0, we are left with only one fixed point. This should remind you of transcritical bifurcation, when as we reach the critical value of the parameter, there is a fixed point that never goes away, which is this fixed point, which is x is equal to 0. However, this is not transcritical, and we will figure out in a moment. So, on left hand side, dx by dt is positive. So, what we are going to see is increase in the value of x. And on right hand side of this fixed point, dx by dt is negative. So, we are going to see a reduction. So, here we have a stable fixed point. Alright, now let us reduce the value of r to negative. When we reduce the value of r to negative, the curve changes slightly, but the system behavior remains quite same. So, we know that no new fixed points are appearing or disappearing. However, when they disappeared, going from r positive to r 0, they disappeared in pairs. This is what informs us that this is a pitchfork bifurcation. I told you when I started this example that this is a very easy example because it is an example of a supercritical pitchfork bifurcation. Let us try to understand why it is called supercritical pitchfork bifurcation, and it is actually a very important kind of bifurcation because this is the kind of bifurcation that we use in case of colony collapses of entire ecosystems, and also in case of catastrophes or outbreaks of insects or outbreak of particular invasive species. Okay, so if we look at this system just analytically, we have dx by dt is equal to Rx minus x cube. So let's call it fx, function x. The analytical method that I taught you in one of the beginning lectures to understand the stability of the system, which is also known as linearization around the fixed point. So we are going to linearize around the fixed point x equal to 0, is to differentiate fx. So if I differentiate fx, I am left with r minus 3x cube, right? And at x equal to 0, this will be equal to r, which is positive, right? So why is it called supercritical bifurcation? And the reason is that in the neighborhood of the critical r, when the two fixed points are collapsing into x equal to 0 fixed point, there happens critical slowing down. So notice two things are happening. Here x equal to 0 is an unstable fixed point. So what it is doing is it is repelling the values, repelling x away from it. So if x in the neighborhood of x equal to 0 is negative, it will be repelled to minus under root r. If it is positive, it will be repelled to under root r. However, as these two fixed points start approaching, what happens is that this repulsion starts slowing down critically. So there is a critical slowing down. It's critical slow in decay, that is what we call it. Critical slow in the repulsion that happens around in the neighborhood. So this repulsion, so things, the dynamism here becomes really slow. And then finally when these two fixed points collapse here, it is no longer repelling. In fact, it becomes an attractor. So this critical slowing is what is linked with supercritical Pitchfork bifurcation. So this is the case of supercritical. Now in what is supercritical about this is minus x cube. When we linearize around x equal to 0, we notice that it is this term that actually determines how things are going to slow down. So for example, if I look, remember linearization. So if I say dx by dt, let's call it function fx is equal to rx minus x cube, and we are trying to linearize it around x equal to 0, around x equal to 0, not at x equal to 0. So first we need to differentiate fx, we are left with r minus 3x square. So at the neighborhood of x, this is what will determine the rate at which things move, the rate at which x, the acceleration and deceleration of x. And this is negative. So r is constant, but this is negative. So what's happening is it is critically slowing down the rate at which f dash x changes as x approaches the fixed point. Now on the contrast, we have another kind of Pitchfork bifurcation, which is subcritical Pitchfork bifurcation, where instead of having critical slowing down around the fixed point, around the critical point, we have an explosion of value, an explosion of speed, which is, think of it like a blowing off of the value. In that case, instead of negative, what we will have is a positive term, something like this, right? Very easily you can understand where the next example will come from for the next lecture. It will come from this. So the next example we are going to take of Pitchfork bifurcation is when fx is equal to rx plus x cube. And this will be a case when around r critical, instead of critical slowing down, we have a blow up. And this is very important in cases of, let's say, insect outbreak, which is another example that I'll be teaching you in one of the upcoming lectures. Okay, let's take a look, let's take a brief look at this system. So we have dx by dt is equal to rx plus x cube. Yeah. So let's find out the fixed points. Now quite similar, the fixed points would be at 0, plus minus under root minus r. So you see this system sort of mirrors what we saw here, except that, so this will be our next system. However, before we proceed, let's make one diagram to summarize how as the parameter changes, this Pitchfork bifurcation system changes. Okay. So what we are going to do is we are going to put the parameter on x-axis, the fixed points on y-axis. Let's take information that we have on this slide. So when r is greater than 0, we have 3 fixed points and minus under root r, plus under root r, and 0. 0 is an unstable fixed point. So, I will show the fixed points with a different color. Let us choose green, a bright green. So, 0 is an unstable fixed point in this case. So, we can show it by dashed lines. And then we have two more fixed points, one is negative, one is positive, and both of them are stable. So, we have a positive fixed point. So, positive fixed point will be on top of the x-axis, negative will be towards the bottom. So, and both of them are stable. So, we can show them with line like so, and they are following root r minus root r. When r is equal to 0, here we have stable fixed point, and when r is less than 0, the stability of the fixed point remains stable. So, this fixed point that was unstable here becomes a stable fixed point, which I am showing by a complete line. So, in this, notice that I show stable fixed points using a line, a simple line, and I show unstable fixed point by showing dashed line. In the exam, if I ask you to draw the fixed points in the diagram of fixed point versus parameter, it is very important that you remember dashed line goes for unstable fixed points and a simple line goes for fixed points. Alright students, this is all for today's lecture. In the next lecture, we are going to cover Pitchfork bifurcation, but another example where instead of drastic slowing of decay, we will have a catastrophic outbreak, blowing off of your variable. Thank you.